everybody, in this video we're going to be talking about graphing polynomial functions and also some modeling. So in the previous videos we talked all about our polynomial functions and we did some graphing, so we're actually going to do more of that today. And then we're going to use a graphing utility to graph and then also build a cubic model from some given data. So our first example, jumping right into it, graph this polynomial 3x plus 1 times x minus 2 squared. And so we worked on a lot of these steps in a previous video, and we're going to put them all together here. So step 1, determine the end behavior of the function. And so what you're going to do here is you want to multiply out the polynomial. In other words, we expand it. And so let me explain what's happening here. So you can FOIL this out. You would FOIL x minus 2 times itself, and then you would have to FOIL the next step as well, and you would end up getting this simplified polynomial. And what you're interested in is this leading term, because that leading term is going to be like your power function, and this is what we learned last time. We know what the end behavior of the graph is based on that leading term and comparing it to a power function. So quick reminder, you had 4 options for your end behavior. So possible end behavior for your graph of your polynomial function. The graph, the 4, either goes up to the right and left, down to the left and right, down to the left, but then up to the right, and then up to the left and down to the right. And then these 4 options were based on this leading term, and so these 2 on the left were if your leading term, that degree of your polynomial, if this was even. So in this case it's odd, but these 2 on the left are if it was even degree. These 2 on the right are if it's an odd degree. And then the difference is whether or not the leading coefficient is positive or negative. And so the 2 on the bottom are when your leading coefficient is negative. So a negative leading coefficient would give you these 2 bottom results. Okay, so just a quick reminder, we did talk about that last time. But for our function here, we have a 3rd degree polynomial, so it's an odd degree, and we have a positive leading coefficient. So that is going to be this situation right here. So positive leading coefficient, 3rd degree polynomial. So we know the end of the graph going left goes down, and to the right toward infinity it goes up. Alright, so now let's find the x and y intercepts of our function. So the y-intercept, just remember, you always just let x equal 0. You can plug that back into our function that we had on our previous slide, and so the y-intercept is 4. Then our x-intercept, you let y equal 0, and then you have to solve for x. And so that one's a little bit more work, because remember this was our polynomial, and if we let this equal 0, it's already factored for us, which is really nice, but we have to solve. And so because this is a product that equals 0, we know if 2 things multiply to be 0, then based on this 0 product property, one of them had to be 0 to begin with. And so that's why we get to this step right here. So we separate the 2 possibilities and we solve each one for x. So then we got negative 1/3 and 2. And those are going to be our x-intercepts on our graph. So step 3 is going to be to determine the real zeros and their multiplicity. So we actually just found the real zeros. In other words, they were the x-intercepts. And we talked all about this also previously, that the real zeros are the same thing as the x-intercepts. And quick reminder, a real zero, also called a root, so a real zero or a root is the number that you plug into your function, and when you plug it in, it gives you 0. That's what we're talking about. And that's why those are our x-intercepts. When we plug them in, it equals 0. And so we had negative 1/3 and 2. And so the negative 1/3 had multiplicity of 1. And we talked about what happens if you have an odd multiplicity, then your graph is going to cross through. So your graph crosses through the x-axis at that point. And if you have an even multiplicity, your graph doesn't cross through, it actually just touches. It touches the x-axis and then goes back the same direction it came from. And so the other real zero had a multiplicity of 2, and so it's going to just touch our x-axis. Okay, so let me remind you how we know the multiplicity also. It was from our function, the way the zeros looked. So watch what happened. We had 3x plus 1 as a factor, x minus 2 squared. So how many times this factor occurred was the multiplicity. So that's why it was 1. And this factor occurred twice. If you want to, you can even write it out twice to see that you could plug in 2 different times. So that's why that multiplicity was 2. Okay, so that's where that multiplicity came from. And then odd multiplicities tell you your graph crosses through the x-axis, and even multiplicity means that your graph just touches the x-axis and goes back. So then the next step, we're going to determine the maximum number of turning points. So remember this, turning points was based on the degree. So we needed to know the degree of the function. And so because the degree of our function was 3, then there's at most 2 turning points. If you take your degree, whatever that number is, you just subtract 1, and that's how many turning points you can have at most. And then step 5, we're going to put all of this together and start to get our graph. And so what you're going to do is, sometimes this is not enough information to get a nice accurate graph. So we're going to find some additional points, and then that's going to help us draw our y-axis more meaningfully. And then where you're going to find these points is you want to actually pick numbers on the different sides of the x-intercepts. So you pretty much think of it as taking your x-axis, plotting your x-intercepts, which we had 2 and -1/3. And let me just fill in some other numbers for us. 0, 1, 3, -1. Okay, so these were our x-intercepts. And so what you want to do is you want to pick numbers around them to give you just some more better points on the graph. So you want to pick some number over here. I'll call these neighborhoods. So you want to pick something in this neighborhood over here. We'll call it neighborhood 1. Something over here, neighborhood 2. So this is a neighborhood, this is a neighborhood, and then something over here, neighborhood 3. So you just want to pick some numbers around your x-intercepts, and that way you're going to get a really nice accurate graph when you plot your points. And so here is what you would get from putting everything together. Okay, so notice if you kind of go back in our steps, the graph does go down toward the left as we go toward -infinity for x, and up to the right as we go toward +infinity for x. So that was our end behavior. So end behavior, check. Then we had our y-intercept of 0, 4, and we have our 2 x-intercepts. And then notice at the -1/3, because it had an odd multiplicity, our graph crosses through. Okay, so we know that this graph starts from down here in the down left, and then it's going to come up and cross through that point. And then we know over here at 2, it just touches. So we know that we had to hit the y-intercept, and then it would help us to find this other point. That's why we plugged in some extra numbers. And so we know that the graph does something where it goes through that point, and then it's going to come back down. It has to touch the x-intercept, but we know that one just touches and then it comes right back up. We know that the graph goes up to the right, And so even without finding 3, 10, we know that this graph has to go right back up. So what we have here is the whole graph put together, but the process that you're going to go through is pretty much what we just talked about. We found our end behavior, so we knew the graph went down to the left and up to the right. Then we plotted our intercepts, and so you would plot those points. So let me do it real quick to sum this up. I'll do it in a different color. So we know that the graph went down here and up here, and then we had this point, and this point. So we know that our graph has to travel through those points. And then from there, we know that we have to cross through this one. So this one was going to cross through, and we're going to just touch this one. So this one's going to just touch like that. And so notice how much of the graph we have now in purple. And so those extra points that we found over here, by just plugging in some numbers into our function around the x-intercepts, those just help us make a slightly more accurate graph, so we can draw the rest of what I have here in red to fill in the remainder of the graph. Alright, so let's try this again. So graph this polynomial function, x minus 1 times x plus 3 squared times x minus 4. So step 1, we're going to figure out what this polynomial function behaves like. And so I'm going to give you a shortcut on this one, which you could use on any of them. If you're just interested in the leading term, just like we were on the last one, because that tells us about our end behavior, you don't actually need to expand this out like we did this time and last time. If you think about what's going to happen from the beginning, notice what you can do. You could say this is going to be x times x squared times another x. So it would be x times x squared times x, which is x to the 4th, which is what we got from expanding it out. So this is a nice shortcut if you just need to know the end behavior. Just be careful if there's any numbers, like I'm going to show you real quick. If there was a number here, like let's say this was 3, you would have to also square that. So that would have became 9. That would have been 9x to the 4th. Okay, so just a quick note on that. Be careful if there is a coefficient there. So that's just a quick shortcut to tell us about the end behavior. So this is an even degree, a positive leading coefficient, and so this graph is going to go up left and up right on the ends. Okay, the y-intercept, if we plug in 0 for x, we get negative 36. And then the x-intercepts, if we set our function equal to 0, and then we go and start solving, each of the 3 factors will get set equal to 0. And so we would get 3 x-intercepts. Negative 1 would be from here, negative 3 from there, and 4 from there. So 3 x-intercepts. And now we have our real zeros and the multiplicities, how many times those factors occur. So this factor, if we write it out really quick from the beginning, we had x plus 1 times x plus 3 squared times x minus 4. So these two factors occurred once, so negative 1 and 4 both had multiplicity 1. Okay, they both had multiplicity 1, which we stated down here. And then this factor occurred twice. Okay, so negative 3 had multiplicity 2. Okay, so now when we go to graph this, these two, let's change colors just so it's a little bit more clear. These two, because they had odd multiplicity, we're going to cross through the x-axis at those points. And then at negative 3, because we had an even multiplicity, we're going to just touch the x-axis and go back from where we came at that point. Alright, so then our turning points, our graph, because the degree is 4, our graph has at most 3 turning points. Okay, so let's plug in some numbers around our x-intercepts. Well, you could just pick random numbers, and then that's going to help us draw our graph more accurately. So quick reminder, we had -3, -1, and 4 as our x-intercepts. So you just need to pick things around them. And so the neighborhoods, there's 4 different neighborhoods here. Something on the left of -3, between -3 and -1, between -1 and 4, and then something on the right of 4. So we could just pick these 4 random numbers, because just to make it very clear, -4 lives here, -2 lives here, 1 lives in here, and 3 also lives in here. But it's going to help us get a better idea of how low the graph goes, because after 4 our graph goes up to the right. Remember the end behavior, it goes up, right, and up, left. So we can pick another number. If you want, you can pick something over here like 5 and plug that in, but you're going to see we're going to get a pretty good graph with these values. Okay, so from plugging in those numbers just right into our function, we're going to get these different y values. So we're going to include those points on our graph. And so these are the additional points that we're going to add to make our graph much more accurate. Okay, so here is the graph of our function. Let's start with what we knew. We knew that the end behavior went up left and up right. So this is the process you would be taking to graph this yourself. Pretend that you cannot see the blue graph. So you would say, okay, the ends of my graph go up left and up right. I had an x-intercept here, an x-intercept here, an x-intercept here, and a y-intercept here. Okay, so you would plot those 4 points. Then you could say, okay, I can kind of tell what's going to happen. I know that -3 was one of the points I just touched, so I can say this much. I could say that the graph just touches. It comes down from up here and just touches. It comes back up. And then I know it has to cross through at -1. So I say, okay, well, it's going to go up and come back down, right, like that. So this point that we found, let me put it in another color. This is just to let us know, like, more accurately how high up we have to go. And then you would say, okay, well, I know I crossed through that point. Next, I have to touch my y-intercept, so you would come down there. So at this stage, we have everything in red already drawn. Okay, we can even draw this part. We know that we come up from the right here, so we're going to go down and hit that point, and we know we crossed through it because the multiplicity was odd. So we know everything in red so far. And so why we found those extra few points is because we just want to be more accurate. We want to know how low we're going to graph this function. And so we would plot those points, and then we would go ahead and connect them. So you can't quite tell by our points that this graph needs to go as low as we drew it. I'll do it in blue. You wouldn't know this without finding more points. You might draw it like this. You might say, okay, I know I got that point, and I know I got this point. So you might end up drawing it like that, which is fairly accurate, but not exactly. So that's why it's good to find more points than we actually found. But this is a really good version of the graph, even with just the points we found. Okay, let's try something a little different. This time we're going to use a graphing utility to graph a function and analyze it. So this is a 3rd degree polynomial. Notice it's not factored, so it's actually a lot harder to draw the graph by hand when it's not factored, because we can't tell the real zeros just by looking. So that's why we're going to use a graphing utility. So this one is 3rd degree polynomial with a positive leading coefficient. So we know the graph's going to go down left and up to the right. So here's actually what this graph looks like using a TI-84 calculator. So I'm going to take us over to the Desmos website and show you how to do this there. Notice it goes down left and up to the right, and it has 2 turning points. And so what we're interested in is the high and low points, the max and min, and also the y-intercept here, and our real zero, our x-intercept. Okay, so our y-intercept we can tell from the function by plugging in 0, and then we're going to go to the website and figure out this real zero, but it's -4.03. And then what you want to do is you want to find some numbers around that x-intercept. And so you can just pick -5 and 3 to just get a more accurate graph, plotting those points. And then we have our maximum. It's actually going to be 15.404, and our minimum is going to be 1.05. So let's take a look. Okay, so here's the graph on Desmos. I just typed it in, and you can actually click on it to get the 0 here, the real 0, so -4.03, and then our y-intercept, and then our maximum, we can click right there, is at 15.042, so that's the highest local max. And then over here is a local min, 1.048. And so this kind of splits up our graph, and we can know it's increasing until this x value, -2.4, and then it's decreasing until 0.5, and then it's increasing again after that. And then some of the other points we found, notice if we just kind of zoom out, it lets us know how low down this goes, how quickly it drops down to the left, and then how quickly it goes up to the right. So then here is our graph, kind of just zoomed in from what we had just seen. And we have our range, all real numbers, because the graph goes up left and down right. And then we talked about it a little bit, but we have our graph is increasing until this x number, and then increasing again after that. So increasing from -infinity until -2.46, and then increasing again starting at 0.57, and then it decreases in between those two values, those two x values, and so that's the interval for decreasing. Okay, one last example here. This one we're going to start with data in a table form, and we're going to actually use a regression model to find a cubic function that approximates these data points. So this represents, in thousands of dollars and thousands of brochures, the number of brochures that a marketing company makes, and then the cost for printing them. So if they make 0 brochures, it actually costs them about $10,000, and you can think of that as like overhead costs, like rent, machinery, things like that. And then 5,000 brochures cost them $12.8 thousand, and so on. Okay, so we're going to draw a scatter plot and then talk about the relation, and it's actually going to be a cubic function. And so I'll actually do that in Desmos as well, but this image is from a TI-84 calculator. Okay, so from the calculator it gives us a regression model, a cubic regression for that graph, and then this is the best cubic function, the best fit. Notice it's x cubed as our highest power of x, so it's a third degree polynomial. And so based on our points, notice that this cubic function, this river shape, is very well approximating the relation between those points. And notice it does have our features from our cube function. It goes down left and up to the right. Alright, so I went ahead and typed in the data points on Desmos, and it gave me the scatter points just like we had from the calculator screen. And so now what I can do is I can approximate this relation using a linear regression model. And the way we do that, or sorry, not linear actually, we're doing cubic regression model, is to type in like a general cubic function. So notice right here what I have. This is a general cubic function. So we have a cube term, a squared term, linear term, and then a constant. A, B, C, and D are what we're trying to find. Those are those coefficients. And we had, from the calculator, we had those values approximated. And then if I turn this on, if you take a look, it approximates that relationship between the points pretty well. Of course, some are above and some are below the line, or the curve, but it's like approximating this relationship very well. Like this point's almost on the curve. Okay, so that is our regression model for this set of data. Alright, then the last thing we're going to do is we're going to use the function we found to predict the cost of printing 21,000 brochures per month. And so we had a cost function that we found using technology, and we're just going to plug in 21 for x into that function, and then calculate that it's about 17.512. And remember, this was in thousands, so the model that we came up with, which was this function, using technology, predicts the cost of printing 21,000 brochures in a month will be $17,512. Okay, so we learned about our polynomial functions and graphing them based on things we've learned previously in behavior, turning points, multiplicity of zeros, and then we actually used technology to find a polynomial model for the set of data points that we had. And that's it. Thanks for watching.